In this video, I want to pick up where we left off on the video about one-to-one, onto, and bijective linear transformations. And it may not have seemed like we had somewhere to pick up. We kind of ended understanding how to determine whether a function's one-to-one, onto, and or bijective. But there's a somewhat natural question to ask based on those definitions. So here's the second example from the video. This linear transformation S from R4 to R3, and it's defined by matrix multiplication. And in the video, what we determined was that, I didn't actually find the reduced row echelon form of the matrix B. We only needed the echelon form matrix. And based on either of these two versions of B in echelon form, we see the pivots, right, in the same spots. And we determined there are not pivots in all columns and there are not pivots in all rows. And therefore, this linear transformation S is not one-to-one and it's not onto. But there is kind of a natural question here. S is not onto. That means that we can't get everything in R3 as an output of S. But what can we get? What vectors can we actually get as outputs? And maybe a less obvious question, but I think still a reasonable one is, well, okay, it's not one-to-one. That is, when we have outputs, there are multiple vectors getting mapped to the same thing. How many? And we'll have to phrase this in some weird sense, right? Because it's always infinitely many, but how many vectors are getting sent to the same place? And so that is our motivation for this idea that I want to talk about of range and kernel of a linear transformation between vector spaces. So range and kernel. So this is going to be defined for any linear transformation between any two vector spaces. And once I define all these things, I'll come back and look at our specific example and see how we understand range and kernel in an example. So the range, also referred to as the image of a linear transformation, is going to be that first extension of an onto function that I talked about. It's going to be the set of all possible output vectors. Another way of writing this is that range of T, that'll be our notation, is the set of elements of W such that there's a vector in the input space V such that T of V equals W. And notice that range consists of vectors from our codomain. They're the vectors that we can actually get as outputs. And this is something you're probably familiar with. Going through an algebra calculus course, you see this notion of what's often referred to as range or image of a function. So this is going to build up off of this idea of one-to-one or not one-to-one. Next, we'll want to look at the kernel, which is also referred to as the null space of a linear transformation. And this is going to be all of the vectors that get sent to zero. Or in other words, the kernel of T, this will be our notation, is the set of vectors in V that T sends to zero. The range was a subset of W. The kernel consists of vectors in V. And this, in some sense, is going to be telling us how many vectors get to sent to the same place. In particular, how many vectors are getting sent to zero. I want to tie this directly into one-to-one and onto, even though hopefully you're already seeing that these are related concepts. We can specify exactly how these are related. T is onto if its range is the entire codomain, right? That's what it means to be onto. You can get every vector in the codomain from some input vector. Less obvious, I think, T is one-to-one if its kernel is just the zero vector. So, this has to be true, right? In the sense that if the kernel is all the vectors that get sent to zero, if more than one vector got sent to zero, then you would not have a one-to-one function. But it also, the converse is true as well. As long as your kernel is zero, this means that you'll have a one-to-one function because it means that your matrix in reduced row echelon form or in echelon form has pivots in each column. So range and kernel are in some sense generalizations of this notion of one-to-one and onto, or they're concepts that allow us to build off of it. And they have this nice connection to one-to-one and onto. But it goes even further. They actually connect directly to things we've talked about previously, and this other name for kernel, null space, is really hinting, or not even hinting, being a bit more than hinting at this. It turns out that the range and the kernel of a transformation are subspaces of W and V respectively. So if we have our linear transformation written as matrix multiplication, so T of V is A times V, then the range of our transformation T is the column space of the matrix, and the kernel of the linear transformation T is the null space of the matrix. So all of that stuff we talked about with column space, null space, row space, all of a sudden it shows up as having a really nice connection to linear transformations and one-to-one onto and bijective linear transformations. So this has all been abstract in the sense that we're talking about arbitrary linear transformations. Let's go back to our example. So we have a linear transformation defined by matrix multiplication. The kernel of this linear transformation is going to be the null space of this matrix, and the range is the column space of this matrix. Now, I think that first statement is more clear as to why it's true. The null space of a matrix in this case B, is the set of solutions, let's write it like this, is the set of solutions to B times V equals 0. That's not how we initially phrased it, but we phrased it as the set of solutions to the augmented system here, but it's the same thing. And this is saying, look, I mean, if B times V is 0, then V is mapped to 0. And so this is exactly the null space of the transformation. What's less obvious, the column space of the matrix is the set of linear combinations. This is how we defined the column space, right? It was the space spanned by the columns. It's the set of linear combinations of the columns of B, but this is the same as all possible things that you can get by multiplying B times some vector. Because when we multiply a matrix by a vector, what we're actually doing is we're taking linear combinations of the columns of the matrix. We're adding columns of the matrix together, and the coefficients that we place on them are based on the vector that we multiply by. And so in our example, this is why the null space of B is the same as the null space of the matrix, or of the transformation, and the column space of B is the same as the range of the transformation, because the range of the transformation is all possible outputs we can get, which is all possible B times V. All right, so far what I've talked about hasn't been allowed us to do any calculations, really. Right? We're trying to understand what these things are. But given an example, how do we find these spaces? How do we find the range of this transformation S, and how do we find the null space of this transformation S? Well, what we've just said guides us in that direction. We want to find, if we're trying to find a vector space, what I mean by that is let's find a basis for it. So finding bases for the range of, in this case, S, and and the null space, not calling it kernel, right? I want to be consistent. Kernel of S. Well, the range of S is the same as the column space of B. How do we find the column space of a matrix? We convert the matrix into echelon form or reduced row echelon form. We identify the pivots, and we take the vectors in the pivot columns in the original matrix. -2, 4, 4, 5, -9, 0. I think I wrote a set notation there. It doesn't really matter. There's not a standard notation for this. -2, 4, 4, 5, -9, 0. So this is a subspace of R3, right? Because that's our output space. And it's the subspace of R3 spanned by these two vectors. It's a plane in 3 dimensions. All right, so finding the range of a linear transformation, once you have the matrix of the transformation and you have it in echelon form, is straightforward. It's the same as finding the column space of the matrix. Similarly, the kernel of a linear transformation is the null space of the matrix. That requires a bit more work to find, but we already have the matrix in reduced row echelon form. And so from the matrix in reduced row echelon form, we know the solutions to this augmented matrix, the system represented by it. So what are the solutions? Well, looking at this matrix, we have free variables in columns 2 and 4. So let's do this workup here. So I'll say that x2 is S1 and x4 is S2. And then when I solve this system, and if I'm not going to write down all the work, I recommend it's a good exercise if you're trying to remind yourself, how do I solve this system where I have B on the left and 0 on the right? Go practice it. Go figure this out and compare your answers to mine. We end up getting that x1 is -13/2 times s1. And we end up getting that x2, not x2, we already know what x2 is. Sorry, I said s1. s2, right? Because this is the column corresponding to x4, which is s2. And then x3 is -3 s2. And so when we solve this, create myself a little bit more space, we end up getting that our solutions are well, our S1 term only has an entry in x2, and our S2 term has entries everywhere else. And so these two vectors form a basis for the null space of B, which is the same as the kernel of the linear transformation. So we've defined these new terms, range, and kernel, and hopefully it makes sense why these are useful things to think about, right? They're expanding on this notion of one-to-one and onto. And we found that, look, ultimately, if we know the matrix of a linear transformation, then the range of a linear transformation is just the column space of the matrix. The kernel of it is just the null space of that matrix, and we already know how to find bases for these things. And we follow that same process. We convert into echelon form or reduced row echelon form if it's the null space, and we either identify basis elements, which columns they're coming from, or we solve the corresponding linear system to get our basis elements.